So in section 1.5, we start looking at some qualities of measurements, and in particular we're going to look at uncertainty, accuracy and precision. And as soon as we start talking about uncertainty of measurements, we're going to start considering how many digits is it appropriate to record? How many digits in my measurement actually have meaningful information associated with them? So we're going to kind of start with accuracy and precision because that's an easier concept, and then we're going to finish with a discussion of uncertainty, and you guessed it, we're going to be talking about significant figures, and we're also going to be talking about our rounding rules. Okay, so a couple of familiar definitions. Accuracy is how close a measurement is to the true value. So it's telling you how far away. If a measurement is highly accurate, it's very close to the true value, and if a measurement is not so accurate, it's a long way from the true value. Now, accuracy is a quality of a single measurement, but it also might be the quality of a group of measurements. And if we've got a group of measurements, what we're going to do is we're going to take the average. All right, so let's have a look at these measurements over here. So look at the ones that have high accuracy. These guys have high accuracy because they are all, they are all in the bullseyes. Individually, they have great accuracy, and as a collection, they also have good accuracy. Now, this is an example where the average of a collection of measurements is used as to define the accuracy. So you can see here that this measurement here is a little bit too high and a little bit to the left, but that's kind of cancelled out when we average it because this one over here is too low and too far to the right. And then we have these two guys here. This one here is too high and too far to the right, but this one is too low and too far to the left. So when you average them all together, the average is actually bang on the target, and we have high accuracy. So that's an important quality of the accuracy. Is it could be a series of measurements, or it could be a single measurement that we're referring to. Now, if I look at some of the qualities of measurements that have bad accuracy, these guys over here, individually, none of them have good accuracy. None of them are anywhere near the center of the target. And as a collection, the average is, it's too high and it's too far to the right. So they have, individually and as an average, they have poor accuracy. The lower set here, if I was to average those out, I've got three that are kind of, or two at least, that are kind of to the left of the desired value. One that sort of, with respect to left and right, is in about the right spot, and then one that's way over to the right. So in general, this isn't going to work. I'm probably going to end up with an average here that would be too far to the left. And then when I look at them here, I've got, two that are too high and one that's one low. So probably on average, they're going to be a little bit beyond the middle of the target. So the average is probably going to come out, to the left and a little bit too high. So again, neither individually nor collectively do these guys have good accuracy. Now, precision is a quality that can't be applied to a single measurement. It can only be applied to a series of measurements. And precision is telling you how close a series of measurements are to each other. So, those guys are very close to one another. So we have high precision. These guys are close to one another over here. So we also have high precision. And these two in the bottom here, in both cases, none of those these collections of arrows are not near one another. So so that's kind of how it is, right? Now, often in a lab, you're asked to comment on accuracy and precision, and it is very important that you consider these definitions. And you can't really just say, oh, it's pretty accurate or it's pretty precise. You need to make a you need to make a numerical comparison of how close your measurement or series of measurements is to the true value, or alternatively how close your series of the values within a series of measurements are to each other. We're expecting, when we ask questions about accuracy and precision, that you refer back to these definitions and talk about it in the context of these definitions. So why do we get low accuracy or low precision? And the reason for that is because we will always observe systematic and random error within a set of measurements. So systematic error is the type of error that results in all measurements in a collection being either too big or too small in a consistent fashion. So for example, when you weigh something or you weigh yourself, you probably experience this, it's like, that's weird, the number's too big. It's always consistently like 15 pounds too big. That's a systematic error. And how you get rid of systematic error is through calibration. So, for me, I normally weigh myself when I go visit my family at Christmas or Thanksgiving, and I hop on the scales, and it always seems to be about 15 pounds more than what I'd like it to be. So what I have to do is I have to bend down and I have to dial back the 0 point by about 15 pounds, and then it gives me the correct value and I'm a happy guy. So systematic error you get rid of through calibration. So sometimes you'll measure a standard and make certain that your measuring device is measuring the correct value, and if it isn't, you'll adjust your measuring device either up or down. Random error is a little bit more complicated. Random error, say there's your true value, is when you kind of get some that are too big, some that are too small, but it's in a kind of random way, and there's no real pattern to it. So why you get random error is because people are only so good at making measurements, and devices can only be constructed so well. So even though you've provided training to the person, you've constructed the device as best as you can, you're using it in a completely appropriate manner, you're still going to get random error. And how we get rid of random error is by taking a large number of measurements and averaging them. And what happens is, hopefully you have as many measurements that are too big as you do too small, and then as a result your average will actually be pretty good because your errors will literally cancel out. Okay, now some numbers, they don't have any uncertainty associated with them, they don't have any error about them. And a good example of this is like a whole number of macroscopic objects. So if someone gave you a bag of pennies, you could count those pennies. Maybe you'd have to do it like a couple of times, but you could state how many pennies you had exactly with no uncertainty. The other types of numbers that are exact and have no uncertainty about them are unit definitions. For example, 12 inches in a foot, or 100 centimeters in a meter. And the reason that those numbers have no uncertainty associated with them is because we made them that way, right? There are exactly 12 inches in a foot because we said so, right? There's no uncertainty about that. So those numbers are described as being exact numbers. Later on, we'll say that exact numbers have infinity significant figures, right? They have infinite sig figs. That's another way of saying that a number is an exact number. So inexact numbers, measurements, always have some uncertainty associated with them. And that uncertainty comes from two places. It's due to the limitations of the person making the measurement, and it's due to the limitations of the device being used. We're not talking about mistakes when we talk about errors. We're talking about the uncertainty that is present even though we are doing everything correctly. So you can see that in this example here is a ruler, and the divisions on this ruler are every 100 centimeters. So clearly the quality of the device is going to affect the quality of the measurement that I can make with this ruler, because 100 centimeters, that's like a whole meter. That's like, you know, a yard or thereabouts. And so, you know, the markings are a long way apart, and so I'm only going to be able to make, you know, measurements of sort of, you know, approximate quality here. So every line here is 100 centimeters, so 100, 200, 300. The blue line is like 300 plus some, right? Now we can be confident that it's like bigger than 300 because we can read those numbers off the scale, but this extra bit out here, who knows what that is, right? We're really just, you know, that's just a wild guess, right? And how well we can guess it is going to be depend on the quality of the ability of the observer, and that's going to be variable. So we're going to define this thing called the significant figures of a measurement. These are the important numbers, the numbers that we have some sort of you know, we have reason to believe are reliable, right? That's what we mean by the important numbers in a measurement. And what we're going to say are the significant figures is the number of digits known with certainty, and these are the ones that basically just means that can be read off the scale. So in my previous example, that was out to 300. I could be certain about the numbers out to 300. And then one and only one estimated digit. So you can't, like, you know, do like, oh, in that other case, you know, 300.056789, because we're guessing way too many digits there. So we're going to say, you know, that you can guess one digit and only one. So we can go one increment smaller than the smaller division on the scale. So whenever we make a measurement, we're only going to include one estimated digit, i.e. that is, we're only ever going to go one more digit smaller than the smallest increment on the scale. So in this case, the scale has markings in the hundreds, so I'm going to guess one number in the tens, right? I'm only going to guess one. So this measurement is a little bit beyond 300, so my allowable values that I could guess would be 310, 320, 330, 340, 350, and so forth. I couldn't guess like 315 because then I'd be guessing down to the ones. I can only guess in the tens, right? Okay, and then it's understood that the number in the tens is a guess, is an estimate. Okay. So that last digit that we record is an estimate, and it's going to vary depending on who has recorded it, and that number will always have some uncertainty about it. It'll always, you know, some people might read that ruler as being 310, other people might read it as being 320. An important thing to recognize is that sometimes we will record zeros purely to let the reader know the quality of our measuring device. So if you look at this measuring device here, it has marks every one. So that means that we can estimate to the point ones, right? We're going to estimate in the point ones. Now, this measurement here is 30, 31, 32, and it looks like it's exactly on 32. But what we do is we include that 32.0, and the reason for putting the 0 there is to let the reader know that we were measuring this on a device that had lines every one, right? So we're recording, sometimes we'll record zeros to let people know how good the device is that we're using, even though mathematically it doesn't change the size of the measurement. There's another little thing that this diagram here illustrates, is that when we're measuring the volume of a liquid, we always measure from the center of the liquid, from the center of the curve of the liquid, which is what we call the meniscus. So we're always going to be measuring from the middle there, okay? And this is important. Sometimes the meniscus will curve up, but we always measure from the middle, so we know that we're going to measure from the top of the meniscus. sometimes the meniscus curves down, but again, we always measure from the middle, so that's what's going on there. And sometimes it's kind of flat, but again, we always kind of measure from the middle. And it depends on what the container is made out of, and it depends what the liquid is in that container as to how it's going to curve, because it's all about how the liquid interacts with the container walls, and we'll talk about that in Chemistry 162. So, when you look at a measurement, you're sometimes asked to determine the number of significant figures, or for what's going to happen to you guys is in your ALEX objectives and in your ALEX tests and quizzes, you're going to be told to write a number to a certain number of significant figures. And so you'll need to know these rules. Now, 3 of the rules are all about how to deal with zeros. And then the first rule is kind of obvious. So our first rule is that anything that is not a zero, any number that's not a zero in our measurement is significant. And then we recognize that there are 3 different types of zeros that might be in a number. There are zeros that could be appearing in between non-zero numbers, and we call those confined zeros or buried zeros, and they are always significant. And you can see here, if you take those out, then we get a very different number, right? 12 is not an approximation of 1002. So we can't just cut zeros out in the middle of the number without changing the meaning of the number. Leading zeros are not significant. And the reason is you can just get rid of them by changing the units. So for example, if I have 0.01 cents, right, or 0.01, let's do it this way, $0.01, I could just write that as 1 cent. Now, you wouldn't want to say that this guy has 3 significant figures, therefore it's a better measurement than this guy, because they're both saying exactly the same thing. So because we can get rid of leading zeros by changing units, in the metric system, in the international system of units, leading zeros are not significant. Now, trailing zeros may or may not be significant, and how we indicate that they are significant is to put a decimal point in our number. So if I write 100, this would have a 1 significant figure, but if I write 100 and then put a decimal point on the end, according to this rule here that says trailing zeros are only significant if the number contains a decimal point, now those zeros are suddenly significant, and this number has 3 significant figures. So if I write the number 200.00, all of my trailing zeros are significant because I got a decimal point there, so this number would have 5 significant figures. So that's how rule number 4 operates. Okay. So as I said, the first rule in determining if the number of significant figures in determining the number of significant figures is to recognize that all non-zero numbers are significant. So 15, both non-zeros, 2 sig figs. Okay. When our number has zeros in it, we're going to use rules 2 to 4 to determine the number of significant figures. So leading zeros are never significant. So you can see this number here has a whole bunch of leading zeros. It looks like there's like 7 leading zeros, but none of them are significant. The only significant numbers in that measurement are the non-zero numbers. And similarly with this guy, the leading zeros are not significant. Both of those measurements have 2 significant figures. They're, of similar quality, or they're of the same quality. They both contain 2 significant figures. Confined zeros, or as I called them, buried zeros, some people call them trapped zeros, whatever you want to call them. I think we pretty much know what they mean, what they are. They are always significant. There's no way of eliminating those guys without completely transforming the number. So these leading zeros are not significant in this number. The non-zero numbers are significant, so that gives you 2. And then we've also got 2 buried zeros, so that's another 2. So we got 4 sig figs in total here. Our fourth rule was that if the number contains a decimal point, then trailing zeros are significant. And if the number doesn't contain a decimal point, trailing zeros are not significant. So leading zeros are never significant. Non-zeros are always significant, so we've got 2 of those. And then trailing zeros are significant if your number contains a decimal point, so we've got another 2 there. So that gives me 4 sig figs total. So in this number here, we've got no leading zeros. We've got 2 non-zeros, so we've got 2 sig figs at the least. And then these trailing zeros are not significant because there's no decimal point. So that number there has 2 sig figs. Now, if I wrote this number with a decimal point at the end, then suddenly these zeros become significant and that number would have 4 sig figs. All right, so most of the time when we have measurements in chemistry, we're going to combine them using some mathematical operations, right? And so what happens when we multiply a number, divide a number, subtract a number, add a number? How does that affect our significant figures? So our general rule of thumb is that the result of our math is can only be as good as the worst number or the worst measurement that we put in, right? And that kind of makes sense. If you measure like 10 things and then then you do some math and you get some output from that math, then the quality of your math is only as good as your worst input, right? It's only as good as your worst number. So that's the principle. How does it actually kind of play out in terms of the rules that we're going to use? Well, there are 2 rules. When we're dividing and multiplying measurements, our answer contains the same number of significant figures as the number with the least number of sig figs. So here we're doing division. This number here, 5 sig figs. This number here, 3 sig figs. So 3 is smaller than 5, so our answer has to have 3 sig figs, right? Okay. When you're adding and subtracting, it gets a little more complicated. Your answer will have the same uncertainty as the measurement with the biggest uncertainty. So say you're like sending a package, right? And you get a box, you weigh the box on a scale and you get a number for that. And you use a big scale for the box because the box is big and heavy. And then inside that you put some contents, and these are like little itty bitty things that you're going to weigh on a smaller scale, and that smaller scale has a greater number of decimal places that you can measure things more to a greater degree of certainty. So the box we measure to be 207.1 grams, and we're guessing about the 0.1. So that means that the uncertainty is plus or minus 0.1 gram. Now the contents we're going to measure on our 3 decimal point balance, right? And we're guessing about this last digit here. Everything else we're reading off the scale, but we're guessing about that last one. So the uncertainty there is plus or minus 1 in the last digit, plus or minus 0.001 grams. So when I add those 2 numbers together, remember the principle, you're only as good as your worst number. My answer is going to be stated to the same uncertainty as the measurement with the greatest uncertainty. So this one is the greatest uncertainty. So I'm going to state my answer to 0.1 grams. So we've got 2 rules, multiplying or dividing. You're going to go with the least sig figs. Adding or subtracting, you go with the greatest uncertainty. And so you probably remember this from Chemistry 139, but you want to just kind of review that and practice a few problems in your ALEX objectives. Okay, so there is a little bit of a problem here. Say I'm calculating a density. Remember that density is mass on volume. So I measure the mass of my object, 26.003 grams. I measure my volume, 25.0 mils. I know that I'm doing division here, so I need to go with least sig figs. That's my rule. So least sig figs is this guy. This number here is 5 sig figs. This number here is 3 sig figs. 3 is smaller than 5, right? So I know my answer should contain 3 sig figs, but when I put it into the calculator, I get that. So what have I got to do is I've got to get rid of those 3 digits on the end there. The question is what do I do with them? Well, in this case, if I just cut them off, 1.04 is a pretty good approximation to 1.04012, right? But what about if those numbers, instead of being 012, were 999? Is 1.04 a good approximation to 1.04999? Or is there a better approximation, right? So the question always comes down to, what do you do with the numbers that you're cutting off? And the answer is, it depends, right? We have to use these things called rounding rules to describe how we're going to deal with this situation where we are truncating numbers. And so these are our 3 rules. If the first number being dropped is less than or equal to 4, do nothing. Just cut off the end of your number. So 1.04012, 0 is less than 4, so I can go ahead and just cut that off, and 1.04 is a good approximation of that number to 3 significant figures. Now, if the first number being dropped is greater than 5, then you're going to increase the value of the last digit. So what about if I had 1.04512? So I got here 512, that's greater than 5. I should point out that this should really be, if you have numbers that are not 0 following the 5, then you're interpreting that as 5 and a bit. So that's interpreted as being greater than 5. So in this case, the best approximation would be 1.05. And then finally, if the first number being dropped is exactly 5, or 5 followed by only zeros, then what you're going to do is use the odd or even rule. And the odd or even rule is this: if your last digit being kept is odd, round up by 1. If the last digit being kept is even, do nothing. So say we have this 1.04500, and we could have as many zeros as we want. We're going to cut this off at 3 sig figs. So we look there and we see that that number is even. So we're just going to truncate it. Okay. Now, if we had, let's just say, I'll just write up here, 1.03500, we want to truncate that at 3 sig figs. Because this number here is odd, we're actually going to go up by 1. So this would be approximated as 1.04. So odds go over, even leave it equal. That's how I kind of remember it. Okay, in your ALEX assignments, they normally tell you the number of significant figures that you need to give an answer to. The other thing they'll do is tell you the number of decimal places that you need to give an answer to. So pay attention to what they're asking for. When we say write a number to 2 decimal places, we mean that we want 2 digits after the decimal point. Okay, it doesn't mean we want a total of 2 digits. So keep that in mind. If they say write a number to 3 decimal places, they mean they want 3 digits after the decimal point, and so forth. All right. What about exact numbers? Those numbers that are either unit definitions or the whole number of macroscopic objects. They play no role in determining the number of significant figures. You can consider them to have infinite significant figures, right? So if you have something like, what is the total length of 3 sticks? Each stick has a length of 30 centimeters. what we're going to say is we're not going to round this off to 1 sig fig because we've got 3 significant figures. This 3 here doesn't have 1 sig fig. It actually has infinity 3 sig figs because it is an exact number. So that's just kind of, exact numbers don't have any role in determining the number of significant figures. If you can't, if you're unwilling to just ignore them, you can consider them to have infinite significant figures. All right, so a lightning fast review of measurement, uncertainty, accuracy and precision, types of errors, and so forth. Not really too much that's new here from Chemistry 139, which is how we were able to go through it so quickly.